Black hole, the largest and the scariest astronomical object in the universe. What will happen if you were to fall in one? Welcome to Experience Machine. My name is Zizap. I am going to take you through a journey in the universe in this bedroom. To simulate this, let's say that you are a standout high school student in the year 2069, and you've been picked as a lucky member to attend Elon Musk's black hole observation mission for free. Now let's meet your crew. This is Derek. He has worked for Elon Musk for 30 years. He is going to be your team leader and teacher. Along with you, we have Frank and Alex. They are all high school standout students, and you four are going to be the member of this journey. Black holes have extreme conditions. Each ship have different ability in different environment. Thus, we need to think carefully which ship to choose, Derek says. And actually, there are three different extreme situations that we need to deal with. First, the extreme gravitational pull. Second, the extreme radiation. And third, the extreme temperature. To deal with gravity, we need a potentially infinite amount of fuel and a really powerful engine. We also need an anti-gravity equipment to not be squashed on the floor. Luckily, we Elon Musk have all of that. Oh, say you can use the deep sea acceleration link. Shut up! Musk have the best equipment. Okay, sorry, sir. And that afternoon, as you watch Elon Musk watching your ship slowly ascend into the sky, you tell yourself, I am ready for whatever happens. As you are ascending into the darkness, there are one question you must solve: which black hole to go to? Now, a typical black hole has three different properties: its mass, spin, and electrical charge. And obviously, our goal is to survive as long as possible. So, a small black hole means shorter time to fall, and that will be not good for us. What we want is a supermassive black hole at the center of each galaxy. That is millions times more massive than our sun. That gives us hours of fall time, which should be plenty enough, right? But don't forget the other two properties. A black hole with a spin means it's literally spinning, will create a disk around its event horizon called the egosphere. And anything on the egosphere is impossible to stay still. That will be really bad for our observation, right? Because say if we are close to the event horizon and the space-time flow of the egosphere swipe us in the event horizon, that will be fatal. We do not want that to happen, right? So we better choose a supermassive black hole without any spin. As of electric charge, it doesn't really matter since our ship is already equipped with photon and magnetic shield. Luckily, the supermassive black hole at the center of our galaxy, Sagittarius A star, has no spin, so that will be our destination. You tell your plan to Derek, and all the other members agreed. As the light speed engine fires, you are finally on the journey. You wake up from the ship, and you can see the black hole outside your window. It's absolutely fascinating. This is the accretion disk. Masses orbit around the black hole on this disk at 90% the speed of light. Matters colliding on each other, creating a billion-degree environment. Derek walked to you guys, and he told you that the first experiment Elon Musk asked him to do was a time dilation experiment. So, what is time dilation? Well, it's a theory from general relativity which states that under different reference frame and different circumstances, time flows with different speed. Now, there are two factors affecting this: velocity and gravitational pull. The greater your velocity, the faster time moves for the outside world. Using this formula, we can calculate that if you were to travel at half the light speed, every 1 hour for you is equivalent to the 84 minutes for the outside world. This positive relationship also works for gravity. If you were to stay 10,000 kilometers away from a black hole with the mass of our sun, every 1 hour of you is equivalent to 71 minutes of the outside world. Fun fact, we can also use this formula to calculate the mass of the black hole in the Interstellar movie. It's roughly 100 million some masses, or this number. Back to our ship. Now our ship is split into two subships. One with Frank staying orbiting the black hole on the Escobel, which is 3 times the event horizon radius, or the Schwarzschild radius. And this bell allows you to orbit safely. Now Derek commands Frank to send a 440 Hz sine wave to the ship every minute on the Escobel, but he didn't explain why. As you waved your goodbye to Frank, you Alex and Derek slowly descend into the deeper part of the black hole. On your way down there, you wouldn't feel anything different, but Frank on the Escobel will observe your ship slowing down, turning red, and finally disappeared into nothingness. But he knew that you guys were alive, so he keeps sending you the signals. At the instant Frank saw you guys disappear, you've reached the photon sphere, which is 1.5 the event horizon radius. Now at this point, light orbits the black hole, which makes it completely dark to the outside world. Standing on the ship, looking outside the window, you literally saw the back of your own head infinitely extending out. It's like one of those double mirror scenes in your dormitory. Light is literally orbiting. How fascinating is that? Now, at the photosphere, exactly half of the sky was a black hole, but as we keep descending and descending deeper and deeper, the blackness takes more part in our field of view, and the universe slowly shrinks into a hole, and when that hole becomes a point, we've reached the event horizon. The distance between your ship and the event horizon are getting closer and closer, but there's a question that bothers you. Looking at the gravitational time dilation formula, you want to find out the time dilation at the event horizon, so you plug in the numbers. Boom! The time dilation is infinite. Wait, does that mean the universe will end its life at the instant I've entered the black hole? Because infinite amount of time should have passed for the outside, right? That doesn't make any sense. With this question, your ship has now officially settled 1 kilometer above the event horizon. You ask Professor Derek for this question, and he tells you, this is the ultimate question that you and me are going to find about. But first, I must do another experiment with Alex. What experiment? The time dilation experiment, darling. What? Are you crazy? Is she going to stay there and are we going down? No, she is going to return back to the Earth. The engine should have enough power though. She is going to find how many millennia has passed for Frank and how many for the Earth. And we are going to go deeper and find the ultimate truth. What? Millennia? Yes, Frank's ship has 2 subships, one for him to go back to the Earth after 3 months. The other stays. It contains a clock that shows how many years have passed. It sure have been a long time. Wow. Now I've realized how vast the universe is. Well, bye Alex, bye. Bye-bye. Bye-bye Steve. We're in the endgame now, Derek says to you. Our ship is exactly 1 centimeter above the event horizon, and according to the formula, 1 hour here equals 49.39 years on Earth. So, Professor Derek, what happens when we enter the event horizon? It's impossible to enter the event horizon. What? Why? I mean, it doesn't make any sense. I mean, where do all the mass that the black hole has sucked went into? It must have fallen into the black hole. It must have crossed the event horizon. Hey, Steve, I know you're confused. Let me ask you a question. What is a star? A star is an astronomical object that is comprising a luminous spheroid of a plasma held together by its gravity. True. Now let me ask you, is a star a thing that contains those plasma, or is a star the collection of those plasmas themselves? Well, that's a philosophical question, isn't it? No, Steve. See, it's not. A star is just a human definition. There are no such things called a star in the universe. It's just plasmas happens to be held by their own gravity, and it glows in the region. It's just us calling them stars. Well, true, Professor. It is also true for a black hole. Black hole isn't an object that's sucking mass in and growing simultaneously. No, it's a region with ultra-high gravitational density. When it's sucking matter, it doesn't suck. Instead, the matter themselves become denser and denser until they become dense enough that they themselves become a black hole region. And we didn't get sucked by the black hole. We are black hole. What do you mean, Professor? We don't fall into the event horizon. Once the region around us has become dense enough, we became the event horizon. Once that has happened, our time dilation will be infinite, that in a single moment, our black hole would have evaporated by something called Hawking radiation. Well, what is that, Professor? It's a type of radiation caused by quantum fluctuation. You high schoolers are too young to understand this, but all you need to know is that it took 10 to the 100 powers years for this black hole to evaporate via that, but for us, it's just 1 second. Oh, thank you, Professor. That solves all my confusion now. Now, the computer says that our region is becoming more and more dense. We are going to become the event horizon in less than a minute. In that 1 minute, you look outside the window, all you see is darkness. You truly appreciate the journey that Dr. Derek has brought you, and you keep thinking about Frank and Alex. Well, they have probably both finished their life by now, and Earth is probably gone. And now, there's only 20 seconds left. In this 20 seconds, I want you guys to like this video and subscribe to my channel. And I want to remind you guys that, first of all, no matter who you are and what your friend and parents says about you, you are still the best of yourself. And second of all, I want to remind you guys that only a small percentage of people that watches this video are actually